So picture this. You're in charge of a $1 billion satellite, hurtling through space, thousands of miles an hour. Everything is running perfectly. And then, suddenly, it's not. But what if that satellite could, feel itself getting sick and tell you exactly what was wrong before it was too late? Right now, the answer is, well, pretty catastrophic. A single tiny failure can turn a game-changing science mission into a very, very expensive piece of space junk. I mean, you can't exactly call roadside assistance when you're in low Earth orbit. The stakes are just unbelievably high. And believe it or not, this problem is only getting bigger. 2,600. That's how many new nano and microsatellites are projected to launch in just the next 5 years. And here's the catch. These smaller, nimble satellites, they just don't have the room for bulky backup systems. So if one little thing breaks, that's it. Mission over. And that's exactly the challenge a team of researchers from the University of Windsor decided to take on. All right, so here's how we're going to break this down. First, we'll dig into the very specific, high-stakes problem they were looking at. Then, we'll see how on Earth you train an AI to be a space mechanic. After that, we'll check out the results, the moment of truth. And finally, we'll talk about what this all could mean for the future of smart satellites. For all the complexity, a satellite success often boils down to doing one thing perfectly, pointing in the right direction. That's it. For communications, for taking pictures, for navigation, its orientation is everything. And all of that depends on one surprisingly delicate little component. And that component is the reaction wheel. These are basically the tiny engines that control the satellite's posture, or its attitude. By spinning faster or slower, they pivot the whole spacecraft with incredible precision, making sure its cameras or antennas are aimed exactly where we need them to be. And here you can see a typical setup. It's an assembly of 4 wheels. The best way to think of them is like tiny, hyper-precise gyroscopes. By tweaking the spin speed of each wheel, the satellite can aim itself any which way it wants. They are the absolute unsung heroes of orbital mechanics, but they're also a huge potential point of failure. So this brings us to a really crucial idea, something called fault detection and isolation, or FDI. It's really a 2-step job. First, you gotta know that something is wrong. That's the detection part. But that's not enough, right? You also have to know what specifically is wrong. That's isolation. Can you tell me exactly which one of the 4 wheels is acting up? And this is exactly why this research matters so much. For all those new, smaller satellites, packing a spare part, what engineers call hardware redundancy, just isn't an option. It takes up too much space, it's too heavy. So the solution can't be bigger, it has to be smarter. It has to be based in software. So that gets us to the core of this whole experiment. If you can't pack a spare part, could you pack a spare mechanic? A digital one? The researchers set out to see if they could train an artificial intelligence to do just that, to diagnose a broken reaction wheel from thousands of miles away, just by looking at the data. So how do you do it? Well, they used a 4-step playbook. First, they build what's called a digital twin of the satellite, basically a perfect computer simulation they could experiment on. Second, they created a mountain of data by running thousands and thousands of scenarios, some where everything was fine and some where they deliberately broke things. Third, they pulled out key patterns from that data, looking for the telltale fingerprints of a failure. And finally, they fed all of this info to a whole team of different AI models to teach them what a broken wheel looks like. Now, this is the really clever part. The AI isn't just looking at the raw data. No, it's smarter than that. It's analyzing the error, the gap between what the satellite is supposed to be doing and what it's actually doing. So it looks at the average error, or the mean. It looks for the single biggest screw-up, the peak. It checks how messy and inconsistent the error is, that's standard deviation, and it even looks at something called kurtosis. Yeah, I know, big word, but it just describes the shape of the error data. Okay, so the digital satellite is built. The data is generated. The AI is trained. Now for the most important part. They held back about 20% of their data for a final exam, to see if the AI could diagnose problems it had never, ever seen before. This is it. Judgment day for our digital mechanic. And here are the results. They tried 4 different AI models. The first 2, a k-nearest neighbor and a neural network, did okay, scoring in the high 30s. But the real jump in performance came from what are called ensemble methods. These are AIs that basically work as a team, combining a bunch of weaker models to make one much stronger decision. And the top performer, the winner, was something called an Adaboost Random Forest, clocking in at just under 59% accuracy. So, what the heck is that? Well, think of it like this. It's not one expert, it's a whole committee of experts. A random forest is already a team of decision makers, and the Adaboost part just means the system pays more attention to the experts on the committee who have been right more often in the past. It's a team effort, and it clearly paid off. So the big question is, why wasn't the score higher? 90%? 100%? Well, these two images tell the whole story. On the left, you're seeing the real data. Each color is a different type of fault, but look at it. It's a messy, overlapping jumble. It's really hard to tell them apart. Now look at the right. That's the AI's prediction. It's trying its best to draw clean, neat lines in a world that is anything but. This shows you just how incredibly difficult this problem really is. And this leads to the question you're probably thinking. 59%. I mean, that doesn't sound amazing, does it? You wouldn't take your car to a mechanic who was only right a little more than half the time. So was this whole thing a bust? Should they just scrap the idea? No, not at all. And to understand why, we just need to change our perspective a little bit. This research wasn't about building a perfect, finished product on day one. It was about finding out if this idea was even possible in the first place. And the researchers themselves had some great ideas about the score. Like we saw in those charts, the fingerprints of each failure might just be too similar. It's also possible the AI needs more clues, maybe data on temperature or how much power the wheels are using. And of course, like any sophisticated tool, these AI models need a lot more fine-tuning to get them just right. So here's the bottom line. This was not a failure. It was a proof of concept. It proved that an AI can figure out what's wrong with a satellite using only performance data and do it way, way better than just random guessing. This wasn't the finish line. It was the starting gun. And I love this quote from the paper because it really just hits the nail on the head. It provides invaluable analytical redundancy. That's the magic phrase right there. It means instead of a physical spare part, you have a smart software-based spare part. It's a software solution to a hardware problem. And that is absolutely critical for all those smaller satellites we were talking about. So, could we see the next generation of spacecraft flying with their own onboard AI mechanic? One that's always on duty, ready to diagnose a problem long before it ever becomes a mission-ending disaster? Well, this research suggests the answer is a definite yes. It's not a finished product, not by a long shot, but it is a really exciting first step toward a future where our most advanced machines might just learn to fix themselves.